Okay, so we're continuing on with the first set of chapter 3 and 4 slides. So I think we just finished up with slide number 35 last time. So in this video, we're going to talk about how to go from percent composition to the empirical formula. And also we're going to talk about how to correctly approach the balancing of equations. So if you remember the empirical formula, that's the lowest whole number ratio of the elements in my formula. It might not necessarily be the actual molecular formula, but at least it tells us the relative number of each atom type in the chemical formula. So that same handout, I think it's the fourth one, with a bunch of different flowcharts on it, also includes this flowchart to talk about how to get from the percent by mass to the empirical formula. So the first thing is we assume that there's 100 grams of total sample. So what that means is from the mass percentages, I just translate it to grams. So if it's 45% carbon, now I say it's 45 grams of carbon. So I'll have a gram amount for each component in the formula, and then one by one for the atoms, I'll use the molar mass for that substance and convert it into moles. So then at this stage, I should have mole amounts of each component in my overall formula. In all likelihood, I won't have whole numbers at this point. So then the last step is to calculate the mole ratio, and I do that by dividing by the smallest number of moles. Basically, we assume whichever one has the smallest amount, that there's only one of those in the formula, and then we're finding out how many of each other element there is relative to that, and ultimately that would give me the lowest whole number ratio, the empirical formula. It's possible that I won't end up with whole numbers at this stage, but if that's the case, then I'll have to do something like multiply through by 2 in order to make that clear out so that I have all whole numbers. So let's walk through an example of how this would work, and then I think I have one for you to solve as well. I think I actually have two for you to solve. So there's a story in this problem about some compound. It doesn't really matter. It tells me the important thing, which is 61.31% carbon, 5.14% hydrogen, 10.21% nitrogen, and 23.33% oxygen. So remember, earlier we were trying to turn the formula into the mass percentages. Now we're doing the exact opposite, and the goal is to find the empirical formula for this substance, which happens to be some stabilizer that typically shows up in sunscreen. So we start out by assuming 100 grams of our substance. So whatever the gram amount, or whatever the percentages were that were given, we've now made them into gram amounts. And then for each substance, carbon's molar mass, hydrogen's molar mass, nitrogen's molar mass, oxygen's molar mass, we'll divide by the molar mass. And then now that gives me a mole amount for all 4 components. And then I want to notice which one of these values is the smallest. And I'm going to say, since it's nitrogen, I'm going to assume 1 nitrogen per, I'm going to say molecule, but really it's the empirical formula. So then basically what we're going to say from there is if there's 1 nitrogen per molecule, if I divide the other 3 values by 0.7288 moles, I should get whole numbers for all of those, because it's basically going to tell me how many carbons are there per 1 nitrogen, how many hydrogens are there per 1 nitrogen, how many oxygens. If there truly is only 1 nitrogen in my empirical formula, then I will get pretty close to whole numbers for all the other values, and that'll be it. Then I'll have my empirical formula. So that's what we do here, right? All of these are the 0.7288 moles for nitrogen, and then the respective values for carbon, hydrogen. Oops, got to scroll down a little bit. Carbon, hydrogen, of course, nitrogen, it's 1 to 1, and then oxygen. Well, this ends up working out pretty neatly, right? I get 7, 7, obviously just 1, and then 2. So that tells me C7H7NO2, right? It tells me that for every 1 nitrogen, there are 2 oxygens. For every 1 nitrogen, there are 7 carbons, and for every 1 nitrogen, there are 7 hydrogens. So that's how I end up with my formula. Okay, this problem, wherever I took the original problem from, happened to want to tell you what this molecule looks like, just for kicks, I guess. That's our answer, right? There's no way that I know what it looks like or anything about its structure. I just know the empirical formula. And in fact, again, it's just the empirical formula. So it may not be the formula of the molecule, it's just that elements are in this ratio. So hopefully that makes sense, and we'll work through 2 more of these just to make sure you're feeling comfortable with all of this. So yeah, I think there's 2 examples. So same story as usual. Go ahead and pause it if you want and work through this on your own, or just keep going. So I've got carbon, hydrogen, and oxygen in this case. It's in percentages, but I'm just going to convert them all to grams right away. So 59.94 grams of carbon, 13.44 grams of hydrogen, 26.62 grams of oxygen. And then, one by one, I'll convert them into moles. So 1 mole carbon, from the periodic table, it's 12.01 grams to 2 decimal places. 1 mole of hydrogen, 16.00 gram. Oops, sorry, I jumped the gun. 1.01. Sorry, my brain was one step ahead of me. And then lastly, 1 mole of oxygen, now 16 grams of oxygen. So grams cancel grams, grams cancel grams in all of these cases, so we'll be left with values in moles. Let's see what I get for these. So 4.991 moles of carbon, 13.31 moles of hydrogen, and then 1.664 moles of oxygen. So now I can divide the carbon and hydrogen amounts by 1.664. Same for the oxygen, but that's just going to give me 1. Let's see what we get. This one is 2.999, so 3. And 7.999, so 8. So then this formula is going to be C3H8O. And when you're presenting the formula, you can just do it in the order that I gave you the components, but the official rule is carbon, then hydrogen, then everything else in alphabetic order, but that doesn't matter all that much. Okay, so that's how that goes. So hopefully that makes reasonable sense. We have 1 more of these to work through as well. So now it's same thing, carbon, hydrogen, and oxygen. So let's get these numbers down. 58.79 grams carbon, 9.887 grams hydrogen, 31.33 grams oxygen. Okay, so same steps, right? 1 mole carbon, 12.01 grams carbon, 1 mole hydrogen, 1.01 grams hydrogen, and 1 mole oxygen, 16.00 grams oxygen. All right, let's get these. So 4.895 moles of carbon, 9.789 moles of hydrogen, and 1.958 moles of oxygen. So we can divide everything by 1.958. Obviously that's 1. 4.895 divided by 1.958. That gives me 2.5. 9.789 divided by 1.958. That gives me 4.999. So what does that mean? Well, it means for every 1 oxygen, there are 2.5 carbons. Well, I need whole numbers in my empirical formula, right? It's the lowest whole number ratio. So effectively what that's telling me is I incorrectly guessed that there was only 1 oxygen in the formula. In fact, there are actually 2. And I can just clear that up by multiplying everything by 2. Because that's saying for every 1 oxygen, there's 2.5 carbons. But that means for every 2 oxygens, there are 5 carbons, and there are 10 hydrogens. So if I get to this point where 1 or more of them comes out as something 0.5, clear it out by multiplying all of them by 2, and then that'll ultimately get me the formula. And here it is, C5H10O2. Still the empirical formula, right? That's still the lowest whole number ratio we could have for this substance, so that's what we get in this case. So that multiplying through by 2 to get everything to a whole number, that shows up once in a while, just when the atom we have the fewest of in our formula has more than 1 of them in the formula, then we end up having to clear things out. And from stuff you'll see from me, either it'll come out as whole numbers or you'll multiply through by 2, and that's really it. In theory, you could have to multiply through by something else, but that's incredibly rare and nothing that I would give you to do. Okay, so just to give you an idea of what we're doing here, in addition to these problems just being good practice to start applying your conversions from grams to moles, this is a pretty standard thing that we do. When we make a new substance, if it's a hydrocarbon, so something with carbons and hydrogens and even oxygen, then we do what's called combustion analysis, where essentially we put it into a furnace that burns it, but then sends the remains through a variety of detectors. And the detectors are basically going to be able to measure the amount of carbon dioxide produced that helps us figure out how many carbons there were in the original substance. Then the amount of water produced will tell us about the hydrogen. Then the amount of oxygen produced, we can kind of figure it out as the last bit of information. All right, and if things get more complicated than this, then we can do a more thorough elemental analysis for things other than carbon, hydrogen, and oxygen. Then there are other ways to go about doing that. All right, so yeah, that's how these ones work. The last topic that I want to go over in this video is how to balance chemical equations. And so you can always do them by trial and error. There isn't much that you need to follow in order to do that, but a little strategy goes a long way. So what I say is identify the most complicated species in your molecule, or most complicated molecule in your equation, and set the coefficient to 1. So we assume there's only one of those, and we figure out everything else relative to that. Something to look out for, and this isn't a hard and fast rule, but look out for homonuclear diatomics like H2, O2, and F2, because those are things that are going to tell you that maybe you are going to need to start with a coefficient of 2 for your most complicated one, and from there everything else should fall into place. Just like with empirical formula, we want to ultimately end up having only whole numbers as our coefficients for our balanced equation, so sometimes one won't work, and then we'll have to figure it out from there. Once you set that first value, then essentially the others are going to gradually fall into place. Let's say that you accidentally decide to start with 2 rather than 1, and then you just end up with all of your balancing coefficients to be even numbers. You can just fix that by simplifying, divide everything through by 2 at the end. But a truly balanced equation for our purposes is going to have the lowest whole number ratio possible. So I picked a few examples already worked out. Sodium chloride plus calcium carbonate makes sodium carbonate plus calcium chloride. I identified sodium carbonate as the most complicated because it has 3 total ions, 2 sodiums and 1 carbonate, so 3 total overall. And then once I knew that I had 1 sodium carbonate, that locked in the sodium count at 2. So that let me put a 2 over here for sodium chloride. And then that means that there are 2 chlorines, so that allowed me to lock in 1 for calcium chloride, and then 1 carbonate also locked me in with 1 calcium carbonate. So that's kind of the process that I follow to get all the pieces to fit, and then once that's all done, I just rewrite it in the correct format with the coefficients wherever they are out front. If there's no coefficient, then there's nothing that I need to do. Here's another example with C5H12 plus O2 makes H2O plus CO2. The last one I kind of figured which one had the most ions. This one, it's pretty clear C5H12 is the most complicated species, so it makes the most sense to make that one 1. That means 5 total carbons on the left, so I can lock in carbon dioxide at 5. It also means 12 total hydrogens on the left, so 12 total hydrogens are needed on the right, so we get a 6 there. And then if I total up the oxygens, it's 5 times 2 from the CO2 plus 6 more from the water, so 16, and then divided by 2 because it's O2, that's how I get the 8 for oxygen. And then I'm all set with 1, 8, 6, 5 as my coefficients. Okay, so I've got, I think 4 of these for you guys to do, and hopefully it'll make reasonable sense. So usual drill, right? Pause it if you want to. All right, so this looks like my most complicated because there's 5 total ions, so I'll put a 1 for chromium 3 carbonate. That means there's 2 chromiums total on the right, so this will become a 2. 3 total carbonates, so this will become a 3. And that set me at 3 total calcium, so calcium chloride becomes a 3. So then I can rewrite it as 2 chromium 3 chloride plus 3 calcium carbonate makes chromium 3. Oops, that's not supposed to be a 3. Chromium 3 carbonate plus, 3 calcium chloride. Let me rewrite that. 3 calcium chloride. Okay, next one. We'll set our first coefficient to be a 1 for C6H14O, clearly the most complicated. That locks me in with 6 carbons and 14 hydrogens, so 7 water. 7 times 2 is 14. Same thing for these combustion-like reactions. add up your oxygen. So it's 6 times 2 is 12, plus 7, there's 19. Well, 1 is already accounted for in C6H14O, so I just need to account for 18 more, but again, it's O2, so this needs to be a 9. So then when I rewrite it, C6H14O plus 9O2 makes 7H2O plus 6CO2. Okay, these last two are going to be ones where if I start with 1, I'm going to get stuck with a fraction, and then I kind of need to fix things from there. So you'll find that 2 will work better. But let's say we start with 1 in the same way. C5H12O, clearly the most complicated. That would lock me in with 5 CO2 and 6 H2O. So it'd be 5 times 2, 10 oxygens, plus 6 more, 16. Well, again, there's already 1 oxygen here, so that would mean that I need to somehow get 15 more from O2, which isn't really going to work all that well. So, right, if you like fractions, then you'd come here and say 15 over 2, and then multiply everything out. If you don't, basically you say, well, I'm stuck with fractions now, let me come back and start with a 2 as my most complicated coefficient. So that becomes a 2, so that'd be 10 carbons, so 10 carbon dioxides. That's 24 hydrogens, so that'd be 12 waters. And now it's 10 times 2 is 20, plus 12, 32. 2 are already accounted for with the C5H12O that I have 2 of, so then this just becomes 15. So if for some strange reason you like fractions, you can balance it with fractions and clear it out by multiplying by 2, but most people usually end up just starting over with a 2 as their coefficient just to make it all work out. Totally up to you. Okay, one more time here. 1, 6, 7. We total up our oxygens again. 6 times 2 is 12, plus 7, that's 19. So now we're kind of in the same spot where I've got O2, but I need to make it work out. So you can either start over or say, well, that's 19 over 2, and I can clear it out by multiplying by 2. Most people don't like to do it that way, but totally your choice. So once you see that it's not going to work out with whole numbers, come back with a 2. That's 12 carbons, so 12 CO2. Then 14 times 2, 28 hydrogen, so the water needs a 14. And now it's going to be 12 times 2 is 24. Oh, sorry, 12 times 2 is, I said it right, wrote it wrong. 24 plus 14, that makes it 38. And so now that divides evenly by 2, so that'll be a 19. So as I said, you can do balancing by trial and error, that's totally okay, but having a little bit of strategy like identifying the most complicated species, I think that'll help a lot. So that's my main suggestion for working on these types of problems. Okay, I think that's it for this video. Now that we know how to balance equations, in the next one we'll start to do calculations where we say for a given mass of reactant, what mass of product do we expect to get out? And so now we'll need to incorporate all of our ideas, how to balance chemical equations, how to interconvert between grams and moles, and how to interpret the balanced chemical equation. So yeah, I'll go ahead and stop here.